Okay, so this is the last part of the Year 2 correlation and regression. In this section, we're going to look at hypothesis testing for zero correlation. Now, you'll have done hypothesis testing in Year 1. There's lots of different hypothesis testing, so don't think it's just going to be the same as that one. I'll explain, first of all, what a hypothesis test is, and then what we do when we're using it with correlation. So first of all, this is, in general, what is a hypothesis test? So a hypothesis test is an act in statistics whereby an analyst tests an assumption regarding a population parameter. The methodology employed by the analyst depends on the nature of the data used and the reason for the analysis. Hypothesis testing is used to infer the result of a hypothesis performed on sample data from a larger population. So what does that mean? Well, a hypothesis is a claim or a statement that you believe to be true. So we're trying to prove or disprove a statement that we believe to be true. Okay? The statement that we believe to be true, we denote by our hypothesis notation there, H0, which we call the null hypothesis. Okay? And this is our default statement. So this is the statement that we believe to be true. Okay? If, for example, you had a coin and you wanted to do an experiment to see if your coin landed on more heads than tails. So you thought your coin was biased. The null hypothesis in this case would be P equals half, because our default statement is that the coin is fair. So the probability of getting a head would be a half. So we always have a default statement that we assume is true. It might be a dice, and we want to work out if the dice is loaded. So in other words, it's coming down on a 6 more often. Your null hypothesis in this case might be that the probability of getting a 6 is a sixth. So we would assume that it's a fair dice. So that's our null hypothesis. It's a default statement. And then we would then have what we call the alternative hypothesis, which is, in this case, it might be P is greater than a half or P is greater than a 6. So we are trying to either reject this. So we're going to either do some statistics to reject our null hypothesis and say that this is true, or we will do some statistics and we will fail to reject the null hypothesis and have to stick with our default statement. Okay? Now, it doesn't matter what statistics we do. We can do different statistics. So in the lower 6, the hypothesis tests that you do is in association with binomial distribution. So it's using probabilities to work out whether the null hypothesis is true or not. We can use other statistics. So depending on what this analyst is doing, the statistician, depending on what statistics that they are doing, will depend on what their null hypothesis is. We are going to use PMCC. We're going to use correlation. to prove or disprove our hypotheses for this particular section. Okay, now it says hypothesis testing is used to infer the result of a hypothesis performed on sample data from a larger population. So what we're trying to do is we're trying to use data based on a sample to prove or disprove whether what we've found for our sample can be said to be true for the population. And in the case of what we're doing now, we're doing that to do with correlation. So for example, the population might be students at Holy Cross. So if you think there are 2,000 students at Holy Cross, all of them together would be considered to be the population. We might want to find something out about that population, so we might take a sample. So let's say we took 50 students from the population of 2,000 and we measured their height and weight, and we plotted a scatter graph and we worked out the PMCC, and let's say we got a PMCC of 0.8. So based on our sample of 50 students, that sample is telling us that there is strong positive correlation between height and weight of our students. Okay? What we need to do is see whether we have got enough evidence to suggest that the whole population's of students' height and weight is also strong positive correlation. So we're using the information that we've worked out for our sample to determine whether there is enough evidence to suggest that our findings will be true for the whole population. And that's essentially what a hypothesis test is. So you perform perform some statistics on a sample and look to see if there is enough evidence to suggest that it's going to be true for the whole population. Now then, if we get down to a bit more specifics to do with correlation, when we calculate the PMCC for our sample, we use the letter R, and that is our sample correlation coefficient. So we've used however many values that we've got, 10, 20, however many values that are in our sample, we use that data to work out the value of R. We can use a hypothesis test to determine whether our value for R for the sample indicates that there is going to be a linear relationship for the population, and the PMCC for the population is denoted by the Greek letter rho, which looks a bit like a P, but it's a bit more sloped and it's on a curve. Okay, so when you write it down, please sort of emphasize the slope and the curve, because your PMCC that you use for binomial distribution from year one, you do actually use the letter P. So it can't look like a P, because that's the probability. It's got to definitely look like a rho. So that letter rho is denoting the PMCC for a population, and the R is the PMCC for the sample. Now our default, so this is our default null hypothesis. So we are always going to assume that there is no correlation. And then we are going to get our sample PMCC to either see if there's enough evidence to suggest that actually there is evidence for positive correlation, or for negative correlation, or for some correlation but not in a particular direction. Okay, now to do this, it says the correlation coefficient for the sample data, so that's our R, is compared with a critical value, which depends on the number of data items in the sample. The significance level, so that's how confident you want to be, and whether the test is a one-tailed or two-tailed. These two are one-tailed, and this is two-tailed. And you look up the critical values in the table. Okay, now here is an extract of the table that you've got. It's on page 191 of the Year 2 Applied textbook. It's also at the back of your formula booklet. So if you turn to the back of your formula booklet, I think it's on the penultimate page after all the binomial distributions. You'll have one table that says product moment coefficients. So if you turn to that, if you haven't got your formula booklet, open Active Learn and turn to page 191 of that, and you'll see the same table. So here's just a snip of it. So you've got down the side, you've got your sample size. So that's how many coordinates you've got in your table for your scatter graph. And then across the top are the significance levels. Okay, so this here is a 5% significance level. And then these numbers here are called critical values. So just to explain, someone asked me what are actually these numbers. I shall try to explain. It's to do with likelihood, really, of getting correlation. So let's say you've got a sample of 2. So you've collected 2 pieces of data. When you plot those 2 pieces of data on a scatter graph, if they were to lie directly horizontally of each other, you'd have a PMCC of 0 because the gradient's 0. If they happened to lie directly one above each other, you'd have a PMCC of 0. Okay? So there's a small chance that you're going to get a PMCC of 0. But there's a much greater chance that it's not going to be horizontal or vertical. If it's anywhere that's not horizontal or vertical, that's going to give you a PMCC of 1, because that's a line. You could work out the regression line, which will go through both points, so you'd have a perfect PMCC at 1. Or if it was somewhere over here, that would give you a PMCC of -1. So if you only have a sample of 2, you're very, very likely to either get a PMCC of 1 or -1. More often than not, it'll be one of them two. If you, however, have 8 points, 4, 5, 6, 7, 8, okay? If you have 8 points, then for those 8 points to lie roughly in a line is much more significant. There's much less chance of getting those points in a line. If you think those points could have just gone anywhere, for them to fall roughly in a line, then there's much more significance to that. So if you go back to that table, for a sample size of 8, if you think of this as being a percentage chance, what this is saying is that there is a 5% chance that you will get 8 points to have a correlation of 0.6215. So there is a 5% chance that 8 points would have a PMCC of 0.6215. Okay, so for example, so if you've worked out your sample and you've got a PMCC of 0.9 for your 8 points, then this is saying there's only a 5% chance that your 8 points are going to give 0.6215. So if you've got 8 points and you've got a PMCC of 0.9 and you only had a 5% chance of getting that number, then there must be something in that. That must be significant. Okay? So this number here, for example, that number there, that's saying that there is a 10% chance that your sample of size 7 would have a PMCC of 0.5509. This number here, there is a 1% chance that 5 points would have a PMCC of 0.9343. So that's what these numbers mean. So what we're going to do is we are going to compare our R value to these critical values here. Okay? And depending on what they are, we will either reject our null hypothesis and say that there is enough evidence of correlation, or we will fail to reject our null hypothesis. So it says, basically, if your value of R shows a stronger correlation than the number from the textbook or from the formula booklet, we're going to reject H0. So if our R value, you've looked up from your table the critical value, if your R value is somewhere close to 1, then we will reject H0 and say there's enough evidence of correlation. If your R value is closer to -1 than the critical value, then we will reject H0. If your R value is not as strong as your critical value, then we will fail to reject H0 and we will have to accept it. Okay, so I'm going to show you the concept of this is much more difficult. I will give you some examples. Not that one. Okay, so let's say that you have taken a sample of 10 pieces of data. So you've got 10 coordinates, you've drawn your scatter graph, or you've stuck in your calculator, and you've worked out that there is a linear relationship with a PMCC of 0.735. Okay, so based on that, based on your sample of 10, you think that the two variables that have got a PMCC of 0.735, that's showing strong positive correlation. So you suspect that actually the population that you took your sample from would also have positive correlation. Okay, so I'll say that again. So you've took a sample of 10 pieces of data from a population. You've worked out a PMCC that is 0.735. So that's telling you that for your sample of 10 pieces of data, you have got strong positive correlation. So you think now, because you've got that actually there must be positive correlation for the population. So your null hypothesis, remember that's always going to be 0, so we're assuming initially that for the population there is no correlation. But based on this, you think actually that there must be positive correlation for the population. So we're going to test at, let's say we test at the 5% significance level. That means that we want to be 95% confident that we are going to make the right conclusion. Okay, so this is our PMCC. So if we look on our table, if you look on your table, if you look down, so if you look on your table, go down to 10, and then across So you go in sample, I haven't got it on here, don't think. No. So go down to your 10 and then go across to your 0.05 and you should see that it's 0.5494. So along from 10 down to 0.05, you should get that value there. That's the critical value. So that's saying that there is only a 5% chance that you're going to get your 10 points to have a correlation of 0.5494. So my critical value is 0.5494. Okay? But my R value is 0.735. So the table is telling me that there's only a 5% chance that my 10 points gave me this correlation, but actually my 10 points have given me stronger correlation. So because my sample correlation is greater than the critical value, my sample correlation is greater than the critical value, this is stronger than this, then there is enough evidence to reject H0 and conclude that the correlation must be positive for the population. So because my sample PMCC is stronger than what the table is saying is there's only a 5% chance of it happening, then that must be enough evidence to suggest that the correlation for the population is not 0 and it is actually positive. Okay, I'll show you another one. Let's say that you have a sample of 15 and you work out the PMCC is negative 0.573. So you've taken a sample of 15 from the population, and using your sample of 15, you've worked out that that has given you a negative correlation of 0.573. Okay, so you want to test to see if instead of the population correlation coefficient being 0, you believe that actually there must be negative correlation for the population. So you decide to do a hypothesis test to see if you can prove that this isn't true and actually the correlation coefficient for the population must be negative. Okay, so this time you decide you want to be 97.5% certain that you're making the right decision, so you're going to test the 2.5% significance level. Okay, you want to be more certain. You will be told this in the question, by the way. Okay, so what we're going to do is we're going to look up from our table where n equals 15 and where the significance level is 2.5%. So you're going to go to your table, you're going to go down to 15, down here, you're going to go to the 2.5% significance level here, and you should get, it should say 0.514. Okay, now note all of these are positive. If you're looking for a negative, then you just take the negative version of it. So the critical value here is negative 0.514. Okay, so that's saying that there is a 2.5% chance that 15 points would give you a correlation coefficient of negative 0.514. But your sample PMCC is stronger than that. So your R value is less than your critical value. R is stronger R is stronger than the critical value. So that is enough evidence, because your sample PMCC is stronger than the predicted critical value, then you can reject H0 and conclude that there must be negative correlation in the population. Okay, I'll show you another one. Let's say you take a sample of 8 and this time the PMCC you get is 0.497. Okay, so it's moderate positive. So you think you want to test to see if there is positive correlation. So you're testing to see if there is actually a positive correlation. Okay, so let's say this time we want the significance level to be 10%. So we want to be 90% confident that we're going to make the right conclusion. Okay, so we go to our table. We want where it's 8 and 10%. So a sample size of 8, we want a 10% significance level. That gives us a critical value of 0.5067. So the critical value is 0.5067. Okay, now this time our sample PMCC's correlation is not as strong as that. R is less than the critical value. R is not as strong as the critical value. Okay, so because this isn't as strong as what it's suggesting it needs to be, then in this case we will fail to reject H0. Okay, there is not enough evidence based on our PMCC for our sample to suggest that there is positive correlation for the population. So all we can conclude is that rho equals 0. We've failed to reject. Okay, so it's much easier than last year's hypothesis testing. Okay, you always need to do this. Okay, so you will get a mark for doing that. Remember to use rho, it's not a p. You'll get a mark for your critical value. You'll get a mark for making some sort of comparison. You'll get a mark for either rejecting or failing to reject, and you'll get a mark for that. And if it's in some sort of context, you need to say something about the context. Right, we're just going to look at one contextual question. A researcher wishes to find out if there is any connection between the length of time young children spend using computers and their reading ability. She collects data on 50 7-year-olds. So this is your sample size. She's collected data on 50, which gives a correlation coefficient of negative 0.3608. Okay, so we've got, this is our sample and it's giving us negative correlation. Carry out a hypothesis test at 5%, so the significance level is 5%, to determine whether there is any connection between time spent on computers and reading ability. Now, in this particular question, it asks for any connection. So what do you think that means? Okay. The questions, if they're in a context, they're often explicit in what they want you to do. So it might say, to determine whether there is positive correlation or a positive relationship. In that case, you'd have one of them. Or it might say, determine whether there is negative correlation or a negative relationship, in which case you'll have one of them. In this case, it doesn't say explicitly in either way. So this is an example where your alternative hypothesis is going to be just not equal to. Okay, so it's not saying either way, it's just looking for correlation. So this is, because of this, you have a two-tailed test. Now there's two differences. One, that's the first difference. The second difference is when you look up your critical value, you have to halve the significance level. Okay, that's the only difference. Everything else is the same. So on your table, you're going to go down the column to 50, and then instead of looking at the 0.05, you're going to look at 0.025. Okay, so that's the only difference. So the critical value you should see is 0.2787. So you're going down 50, and then along, instead of to 5%, because it's two-tailed, you're going to look up 2.5%. You should get 0.072787. Okay, now because you have got a negative coefficient for your sample, we're going to take the negative value. Okay, so it's only difference. That is the first difference, half in the significance level. It's the second difference, that's it. Then we're going to do exactly the same again. This is stronger than this. R is less than the critical value. R is stronger than the critical value. So because the sample's correlation is stronger than the predicted, then we can conclude that we can reject H0. So we can reject H0. We can say that rho is not equal to 0. So I'm not saying that it's negative. I'm just concluding that it's the alternative hypothesis. And then because it's in the context, I'm just going to say there is a connection between time on computers and reading ability. Okay, so I'd like you to pause the video now and see if you can work through those 4 questions. I'll tell you the answers in a second. Okay, the first one was one-tailed. Your critical value was 0.3783. So because this is more than this is stronger than this, we can reject H0 and say that rho is greater than 0. Second one, two-tailed because of this, which means you're going to look up from 1%, from the 1% column. So you should have a critical value that is 0.5155. So because your sample is not as strong as that, then we fail to reject H0. So therefore we can just say that rho is 0. Third one, one-tailed, 5% significance level. You should have a critical value that is negative 0.4409. the sample is stronger correlation than the critical value, so you can reject H0 and say that rho is less than 0. And then the last one, two-tailed, 5%, so you're looking up at the 2.5% mark. Critical value, negative 0.3739. So I've just taken the negative version because this is negative. So because your sample is stronger correlated than the critical value, then we can reject H0 and say that rho is not equal to 0. Okay, so hopefully you followed that and you did okay. Right, if you have a go at this last question, and your teacher will tell you the solutions. So give it a go. And then there are further practice on page 10. Okay, that's the end of the video.